kinetic parameters. We need accurate data, which are used, in fact, to constrain the model. We want this data to be accurate so that we can really constrain the model. So we have really a constant interaction between experimental data and modeling. And to constrain the model, we are using both global parameters and detailed information. Global parameters consist of ignition delays, which are mostly sensitive to initiation reactions and reactions of radicals with molecular oxygen, and burning velocities, which are mostly sensitive to fluxes of H atoms. We also use different types of reactors, shock tubes, plug flow reactor, perfectly stirred reactor, and flames. For some of the flames, we are aware of probe perturbation that can cause some difficulties in the interpretation of the data. For the modeling, the kinetic modeling is performed using the Chemkin computer package. And so the kinetic reaction mechanism consists of a modified Arrhenius equation of this kind. And we also take into account the pressure dependency of these reactions. We provide the forward rate constant, and the backward rate constant is computed from thermochemistry. Reaction mechanism has a strong hierarchical structure. It is based on the oxidation of a range of hydrocarbons and oxygenate fuels that we studied in the past. So the core mechanism is the hydrogen-oxygen submechanism. Then we have the C1 subscheme, C2, etc., up to about the size of the fuel that we are studying. I will show you some results in relation with ground transportation. Methyl esters are structured like this simple one, methyl octanoate. So we used methyl octanoate, which is not a very big molecule, to represent biodiesel. And I will show you some example later on. So we also used some mixtures of methyl octanoate with either diesel fuel surrogate or also with ethanol. As I told you before, there is an interest of mixing methyl ester with ethanol because ethanol is relatively soluble in this kind of chemicals, whereas it's much more difficult to dissolve in hydrocarbon mixtures. So we studied this fuel mixture in a jet reactor at 10 atmospheres over a range of temperature from 560 K to 1160 for a short residence time of 0.7 seconds. And the experiment been performed for several equivalence ratio from fuel lean, excess of oxygen, to fuel rich, excess of fuel. So in these conditions, I will show you that in the next slide, the fuel is reacting rapidly, and it leads to the formation of many intermediates and oxygenates like formaldehyde, CO. The mole fractions were measured for a range of species, the fuel, oxygen, hydrogen, water, carbon monoxide, carbon dioxide, formaldehyde, methanol, methane, ethane, ethene, acetylene, acetaldehyde, which is an important product of oxidation of ethanol, propylene, 1-butene, butadiene, and some 1-olefins, higher aldehydes and unsaturated methyl esters, methyl propanoate, butanoate, pentanoate, hexanoate, and heptanoate. So we compared these experimental results with those obtained previously for the oxidation of other methyl esters, and well, we found that results were pretty similar. And this new set of data was used to try to validate a detailed chemical kinetic reaction mechanism for the oxidation of this blend. The size of the model is given here, so it's about 1,000 species and a bit less than 5,000 reversible reactions. So we could measure these mole fraction profiles as a function of temperature. So the symbols represent, the large symbols represent the data, and the lines and small symbols correspond to the modeling results. So if we look at this first figure here on the left-hand side top, we can see that there is a strong consumption of methyl octanoate. So this is the cool flame, negative temperature coefficient, and then transition to high temperature. And what is interesting is to notice here that also ethanol is oxidized under these conditions. And this is an interesting result, because normally if we were oxidizing ethanol in these conditions alone, it would not react at all, because it has an octane number which is real high. Well, besides the different intermediates, I would like to point out that we have this formation of acetaldehyde here, which is relatively important, just below that of formaldehyde. And these are the unsaturated methyl esters which we are observing under these conditions. So again, what is an interesting feature when we oxidize this blend is that ethanol is oxidized under the cool flame regime, whereas normally we should not see a strong oxidation. So what's the reaction pathways explaining these results? Well, the fuel is first attacked by radicals, mostly OH radicals. You produce a first radical which is peroxidized by reaction with O2. You get this peroxy radical. By internal isomerization, transfer of an H atom, you get this intermediate radical, which can also be peroxidized by addition of O2. You get this one, and by a second H atom transfer, internal H atom transfer, you get this dihydroperoxy intermediate, which can decompose, produce an OH radical and a ketohydroperoxide. So this OH radical will then reinitiate the reaction here, and so the overall oxidation is starting to get faster, and by decomposition of ketohydroperoxide you get another OH radical which even increases the reactivity of the system. And because methyl octanoate is relatively very reactive under the condition of this study, it will provide these radicals which will attack ethanol. And in every system where there is one reactant which is much more reactive than the others, the radical produced through the oxidation of a most reactive component will feed the reaction of oxidation of the less reactive component. We could argue that it's the same with when you want to compare natural gas, which has higher hydrocarbons, alkanes in its composition compared to pure methane. There is also interest looking at the it's a bit too big. There is a, let me see if I can do better. Yeah. So there is an interest in looking at the evolution of the concentration of acetaldehyde when you oxidize this type of mixture containing ethanol, because it's well known that during its oxidation, ethanol is producing acetaldehyde. And we can see that here from this first line to the last one, we increase the concentration of ethanol in the fuel mixture. And at the same time, we also increased maximum concentration of acetaldehyde during the oxidation of this fuel mixture. So increasing the initial mole fraction of ethanol in the fuel always increased maximum mole fraction of acetaldehyde. And acetaldehyde is a toxic. It is also responsible for the formation of peroxyacetyl nitrate. So once you have ethanol, which is unburned, it will be released in the atmosphere, and either in the atmosphere or in a three-way catalyst, it will be oxidized, produce this radical which then produces acetaldehyde. Acetaldehyde is very reactive. The hydrogen atom here on the functional H atom here is very easy to abstract. So you get this radical, which can be peroxidized, produce this peroxy radical, which react with NO2 to produce peroxyacetyl nitrate, which is a pollutant. But peroxyacetyl nitrate will be transported in the troposphere, and at some stage it will decompose and release NO2 again, far from the initial formation, the place where it has been initially formed. Then it's a transportation of pollution outside the region of production. And then NO2 is released. NO2 is photolyzed by sunlight, produce an oxygen atom, which react with molecular oxygen to produce ozone, and that explains the increased production of ozone in areas where, for example, traffic is not important. We did similar experiments with butanol, which is also proposed as a biofuel, and it was similar. So methyl octanoate is reacting here, and in the same temperature region, we have also a cool flame oxidation of butanol. And you can believe me, if we were oxidizing butanol itself alone, we wouldn't be able to observe this cool flame. So this cool flame is really responsible from the interaction between the two fuels. And similarly to what we showed before, we have all these unsaturated esters which can be released in the atmosphere. We use also methyl octanoate to represent the biodiesel fraction of a fuel. And so we did many experiments. I will just illustrate this with these three different figures. So to represent a B30, 30% of bio-derived component of esters, we used a mixture of normal decane, methyl naphthalene, and methyl octanoate. And we oxidized this mixture in the lab, and these are the large symbols that we see on these figures, and we simulated these experiments. You can see that the model tend to represent fairly well the data, and also for the products, and even for some intermediates like formaldehyde, which is formed here in the cool flame, but also at higher temperature. And then these species, CO, CO2, water, and some hydrocarbon intermediates and formaldehyde were compared to what we could observe with the real fuel, and we could see that there is a good match between the data. We did similar things with jet fuel. I won't have time to show you that today. Because aldehyde are very important intermediates during the oxidation